Okay, so now that you've seen the hard way and the easy way to approach Atwood machines, or really any systems that are moving together with the same acceleration, let's approach this problem and approach it like this system. So if we assume that m2 is going to be greater than m1, we're going to assume that this system is going to move in that direction. And we are going to assume that that direction of motion will be positive. So on the right side, our positive direction is actually down. On our left side, the positive direction will be up. So we are going to apply Newton's second law to the system. So that's going to be the total mass times the acceleration of the system. So we just have to sum up all of the forces, and the ones that are going to be making the system go, and we are going to look at the ones that are going to make it slow. So looking at that, we see, according to our free body diagrams, that these two tension forces are actually going to cancel each other out. And we're left with this force and this force. So when we add that, we can just say m2g is going to make it go, and then m1g is actually going to have it slow some. And then the total mass is just going to be m1 plus m2 and the acceleration of the system. The acceleration of the system, then, just do your algebra, m2g minus m1g, all over the total mass, m1 plus m2. And we always like to clean it up a little bit, and we say m2 minus m1 all over m1 plus m2 times the acceleration due to gravity. This way you can kind of look and see that this acceleration depends on a ratio of those masses and the acceleration due to gravity. Now if we want to find the tension in the string, we can remember that that tension is going to be the same throughout the entire string from side to side, because we're assuming that it is a massless or very, very, very light string, and we're also talking about the pulley being massless, just to simplify the problem in the beginning. So here's our acceleration. Here's our free body diagram I chose for mass 1. We have the tension going up and then the force of gravity on mass 1 going down. So we will just apply sum of all the forces, and it's m1 times a. And we see that we have tension going up, and then minus m1g is all equal to m1a. Then, of course, we're going to plug in this expression down here for a, and we can bring over that we'll wait and do that. m2 minus m1 over the total. Now, there's some really fun algebra that I want you to try to do. I want you to pause the video, and I want you to come up with this expression using some algebra. It's good mental gymnastics. Alright, so go ahead, pause that video, try this in your notebook, try and get this expression for tension to look like this. And then unpause when you check it. No cheating. Okay. Okay, so here's all the algebra that gets you there. And again, that was using the expression for your acceleration of a equals m2 minus m1 over m1 plus m2. And now that we are in Physics C, we look at extreme conditions. We look at it and we say, hey, well, what would happen if m1 was way bigger than m2? What would the acceleration look like? So if m1 was way bigger than m2, what you would do is, like, this would be really negligible and it would kind of fall away. And what would you be left with? You would be left with negative m1 over m1 times g, which boils down to negative g, which just means that if m1 was so big, it would just cause it to fall like it was in free fall. And then what would happen if m1 equals m2? You would have your acceleration equal to 0, because this acceleration equation would just turn into m minus m all over m plus m times g, which of course this turns into 0. And if they're equal, then they wouldn't go anywhere. Okay, so there's an Atwood machine. There will be one more example that I need you to go through. Thanks.